Hello, and today we're going to be talking about the sun. Actually, this is Sun Part 1. I'm not sure how many parts there are going to be, but I'm trying to break it into smaller units. The first thing I want to tell you is that please, under no circumstances, naked eye, telescope, binoculars, whatever, please never look directly at the sun. You guys have probably all played with a magnifying glass at some point, and you see what happens when you take a 3-inch piece of light and you focus it down to a point. Your eyes are not supposed to look at the sun. They're not designed to look at anything that bright, and you can cause temporary and maybe even serious total permanent damage to your eyes. So please don't ever look directly at the sun. Always use some sort of eyewear that will protect you from hopefully more than 90% of the sun. I know we have the telescopes that are up on a roof of our building. Our school building actually have a lens that puts up there that blocks out 98 or 99% of the sun's rays. So only 1% gets through, so it doesn't actually hurt the electronics. But anyway, this is a picture from the sun. This is actually from a site, I can't remember what it is, but we'll be using it when we actually get to the solar system. 9 planets, 9planets.com, and this is their sun picture. I found another picture very much like it, talking about the layers of the sun. Now, we're not really talking about the layers of the sun in this particular part, but we are going to talk about, and I'll show you those in a second. Most of the movies and pics from the PowerPoint that I took these actually are coming from the Solar Heliospheric Observatory, or the SOHO site. If I go back to here, this is the site that I'm talking about, and you can see it's got lots of really cool things. It shows you the sun now, it shows you the sun where we block out things, but it works out pretty well. Okay, so let's go back into here. SWABATs, students will be able to. The only two things we're going to do after this short section for part 1 is know what the general characteristics of our sun would be, and then how do these surface and atmospheric features from the sun actually affect the Earth. Here's another picture showing the eye. If you go look at my Astro Tools Part 1 show, this is talking about the iris and the fact that when you use a telescope that has an opening maybe 100 times this size or 1,000,000 times of this size, the lenses of the mirrors are actually being utilized so they can focus the light of that telescope into this small little opening. In reality, it's taking the small little opening, which is your iris, and making it as large as the front of your telescope. Pick these guys off of that SOHO site. These are my forest park colors, blue and green. It would be nice if they had a silver one in there too, but that'll work. Okay, what are some of the general characteristics for our sun, or one of the stars? First thing, has a diameter of over 108 times the diameter of the Earth. If you can remember this number, 110, that'll work. Taking a look at this picture, looking at this box, there's an enlargement here. This is the Earth and this is Jupiter. You can see Jupiter is much more massive than the Earth, showing sunspots, which we'll talk about in part 2. In the background, there is the Earth, and you could take 108 of those and put it across this way. You could put 108 across this way, and if I just started to draw, you could imagine how many I could get if I started covering every aspect of this sun. But the sun is a lot bigger than the Earth. Okay, some other characteristics we have to cover. Mass. Mass of the sun's about 2.10 to the 30 kilograms. That's a 2 followed by 30 zeros. It's a very large number. In comparison, the Earth is 6 times 10 to the 24th. And if you take a look, that's basically 3 times and then 6 times. It's about 300,000 times more massive than the Earth. It is very large and very massive. 99% of all the mass of the solar system in that star. Composition, about 70% hydrogen. Hydrogen is the #1 element in the known universe. 90+% of the known universe is hydrogen. Our sun now has about 30%, 28%, 2 points shy of 30% helium. Our sun is fusing hydrogen into helium. And we'll talk about the rate of that when we actually get to the core. But it's fusing a tremendous amount of hydrogen every single second of every single day, 7 days a week, 24 hours a day, 365.25 days a year, and it's been doing so for about the last 4.6 billion years. It's been able to turn about 30% of the hydrogen into helium, and then 2% other things like iron, gold, some other things that are out there. Distance, on average, the sun is 150 million kilometers, 93 million miles away from the Earth. That works out to about 93 million miles. This is also called an astronomical unit. When we actually start talking about distances in space, miles, kilometers don't really work anymore. I really don't know what 93 million of anything is, and I certainly don't know what 150 million of anything is. So what we do is we just say, okay, these two numbers, as big as they are, we're just going to divide them by themselves, and we're going to call it an astronomical unit. So the Earth-Sun distance in our solar system is called an AU. This, sooner or later, when we get to stars, will actually be too small also, and we'll have to change it over to light year. But this is a unit we use in our solar system. It goes all the way out to Pluto and beyond. Pluto's around 39 AUs. Jupiter about 5.2. We can go all the way to 0.39, which is Mercury, and we're 1.0, which is the definition of this thing. Okay, we know that the sun is a sphere. We also know that it does rotate now. Taking a look at the surface of the sun, it'd be nice if there was a North America. Notice that I don't have a South America on there. But it'd be nice if there was a North America that we could actually watch move. Rocky Mountains, Appalachian Mountains. And then we have the Mississippi River. But it would be nice if we had that, because then we could sit here on the moon, or we could sit here on Earth, and we could watch the sun rotate. But the sun can't do that, but it does have something on the surface. It does have these sunspots. In viewing sunspots, sun rotates on its axis. It rotates primarily as a very hot ball of gas. So because of that, it can rotate at different speeds. But on average, it rotates once every 27 Earth days. Equatorial rotation, because it can rotate a little faster, about 25 days per rotation. Poles, a little bit less likely because of speeds, rotates about every 36 days. So if you take all the mass that's in the equatorial regions and you take the speed or the slowness, the lack of speed for the poles, it averages out to about 27 days average. Okay, because it is a gas ball, it actually swirls. It has high pressure zones for meteorological lovers, and low pressure zones similar to those that occur on the Earth. This is a couple of pictures. This is actually showing you an AU. AU is the sun to the Earth. If we go out to Mars, it's about 1.5 times the distance. It's called 1.52 AUs. If we were putting Jupiter out there, it'd be 5.2. Saturn's 9.5. And like I said, we could go all the way out to Pluto, which would be about 39 AUs. This is a picture actually showing you the sun rotating, and around 25, almost 26 days along the equator, 36 days around the poles, 60, it's around 31 days. But if we average all this together with most of the mass being here, that's how we come with this 27-day average for the sun's rotation. It does have banding because of magnetic storms that are going on. What happens is the equator is moving at a much faster speed, so these fields actually get tugged and pulled, and you can see they can actually get wrapped around, and this is where it starts causing problems with solar storms on the surface of the sun, likely places to find sunspots, which again we'll talk about later. Temperature of the sun, it is extremely hot. One of the limiting factors of us ever going to visit a star is the heat of the surface. It would melt, vaporize, incinerate anything that's around. On the surface of the sun's around 6,000 degrees Celsius, and it's going to give us sort of a yellowish orange color, which you can sort of see in all the pictures that are up there. The center core is a bunch hotter. We need about 10 million degrees for nuclear fusion, and our sun has an extra 50%, about almost 16, let's say 15 million degrees Celsius. At that speed and that much pressure, that much temperature and that much pressure, the speed of the hydrogen that's in there is moving fast enough to fuse, nuclear fusion. You can see the core temperatures, you can see some of the other zones, and as you get farther away from the core out and toward the surface, it does cool off, and that would get to about 6,000 degrees. Okay, how does the sun actually affect the Earth's atmosphere? This is, anytime you see a picture of the solar system or the universe, it is probably not drawn to scale. Remember, this thing is about 1/108 across here. It is 93 million miles away. This should not be anywhere on this screen. Should be way off the screen in that picture. But what it's trying to show you is the magnetosphere of the Earth. Because of our spinning liquid metallic core, we think we actually have this. Well, actually, we know we've got the magnetic field, but we think it's because of the spinning core. And what happens is it spins out, coming out of the South Pole, and then loops around into the North Pole, and it sort of builds this pressure zone of magnetic field. The back side gets blown away by the sun, the front side gets compressed by the sun, and this is called solar wind. I can probably write that on there. So we go in there with white, and we go in there and we write this is going to be solar wind. And it goes flying in, and it pushes this side of the magnetosphere in. But what happens is our magnetic pole actually pulls a lot of this energy, this charged particle material, pulls it into the Earth, pulls it into the polar zones. This is a picture of the incredibly violent outside of the sun called the corona. This is a picture of a coronal, probably should pick a different color. This is a picture of a coronal mass ejection, which has actually made a lot of news lately with solar wind and hitting the Earth and actually causing tremendous auroras. Here in DC area, I still have not seen any. We have a lot of artificial light in our night sky, so it would have to be pretty bright. And by the time it actually gets this far south, the auroras tend to be pretty dim. So I really need to drive 30-40 miles west of here, go up in the Appalachia and see if we can see these, but I can't do that during the school year. So this is a picture from Soho where they put a metal disc over in front of the sun. This gives you the size of the sun itself. But what you're seeing is the corona, and you're seeing large storms throwing out millions and millions of tons of material out into space. It gets really interesting when it comes out in our area. You can see this is going perpendicular to us, but it's kind of cool when it comes out this direction because then it really affects the Earth. I guess if you play with electronics and other things, it's probably not the coolest thing. What does it do when it actually comes in and hits our atmosphere? Well, it lights it up sort of like a fluorescent light bulb. And because of the nitrogen and the oxygen and the water vapor and the other things that are in our air, we get this tremendously colored, beautiful, lit up atmosphere. If you've never seen one of these, auroras are incredibly cool things. They come in all different shades, and you can see there's some more colors down here. They come in green and lighter green. They come in blue, they come in red, they come in purple, they come in white. They come in lots of different directions. You can see from all these pictures polar regions benefit from these tremendously. The closer you are, and actually right at the North Pole probably doesn't work as well. As you can see, it doesn't seem to come right at the North Pole. It's a band probably right in this area and right in this area that get most of them. Most of the auroras, they're called Aurora Borealis in the north and Aurora Australis in the south. This is the northern light, Aurora light, Borealis meaning north, and this is the southern light. But you can see it actually, it forms a little like a ring around the polar area, maybe around the Arctic Circle and the Antarctic Circle. So if you're right at the North Pole, Santa Claus probably doesn't benefit from these auroras as well as some other places. Okay, so the last thing I want to show you is I want to show you a little bit about these, because these are still images of a shimmering, shaking, spinning, swirling light show. So if we go back to here, sorry, wrong browser, and we go into space weather is a pretty good place to see. You can actually see pictures of the sun on any particular day. You can also see weekend solar flares. Sometimes they even have it in its sound. I guess I could try to play this and see what it does for us. It doesn't seem to be doing anything. Maybe here we go. So this is the way a solar storm sounds. And if we go to here, this is the way they can look. And you can see it's amazing show. And again, we've got snow in the picture. But if you're located by the poles and you live far enough away from lights, you can see these fantastic shows. You can even see when a full moon, at least it looks like a full moon's in the sky. Look at how much light it's producing. But we still get this beautiful view. We scroll over to here, come in lots of different colors. There's that picture of the house again. Flowing streams, flowing sky. How can you get any better than that? I think that was a car. Even the horses can be out there enjoying it. And again, almost any color you want. Okay, Aurora Borealis, caused by solar wind hitting our atmosphere. It's part of an unromantic view of an incredibly beautiful show. Thank you very much for coming out. Appreciate it. Bye.